Good evening, everyone, and welcome to the Droning Professor. Tonight we're going to learn about what happens to time near a black hole. So as you make yourselves comfortable, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. So tonight we're going to talk about something that sounds like pure science fiction, but is actually stone-cold physics. What happens to time near a black hole? And I know what you're thinking, great, another lesson where someone's going to tell me that time is relative and my brain is going to hurt. Well, yes, your brain might hurt a little, but I promise to make it as painless as possible. Think of me as your intellectual anesthesiologist. Let me start with a question. Has anyone here ever been late to class? Of course you have. We all have. Now imagine if you could actually blame physics for being late. Not traffic, not your alarm clock, not the fact that you hit snooze 17 times actual, legitimate, Nobel Prize-winning physics. Well, near a black hole, you could do exactly that. You could show up to class 300 years late and honestly say, "It's not my fault, it's general relativity." Your professor probably still wouldn't accept that excuse, but at least you'd be technically correct, which is the best kind of correct. Now, before we dive into black holes specifically, we need to talk about time itself. And here's the thing about time that's going to blow your mind. Time is not what you think it is. We walk around treating time like it's this universal constant, ticking away at the same rate everywhere in the universe. 1 second in New York is 1 second in Tokyo, is 1 second on Mars, is 1 second near Alpha Centauri, right? Wrong. So wrong. Catastrophically wrong. Like thinking the Earth is flat, levels of wrong. The person who first really understood this was Albert Einstein, and he figured it out in 1905 with his special theory of relativity. Now, Einstein was 26 years old when he published this paper, which means he revolutionized our understanding of the universe at an age when most of us are still trying to figure out how to cook something other than ramen. The man was working as a patent clerk in Switzerland, examining other people's inventions during the day, and then going home and casually destroying 300 years of physics in his spare time. Talk about a side hustle. Special relativity told us that time is relative to the observer. If you're moving really fast, and I mean really fast, like a significant fraction of the speed of light, time slows down for you relative to someone who's standing still. This isn't a trick or an illusion. Time literally passes more slowly. Your watch ticks slower. Your heart beats slower. Your cells age slower. Everything about you experiences time at a different rate. This effect is called time dilation, which sounds like something a villain would use in a superhero movie, and honestly, it kind of works like that too. The classic thought experiment is the twin paradox. You have two identical twins, let's call them Alice and Bob, because physicists are incredibly creative with names. Alice gets on a spaceship and travels at 90% the speed of light to a star system 10 light years away and then comes back. Bob stays on Earth, probably eating chips and watching Netflix. When Alice returns, she's only aged a few years. But Bob is decades older. Alice could come back and attend Bob's retirement party looking like she just left for a long weekend. This isn't science fiction, this is real physics, confirmed by countless experiments. But here's where it gets even weirder. Special relativity only deals with objects moving at constant speeds in straight lines. What about acceleration? What about gravity? Well, Einstein spent the next 10 years thinking about that, probably while doing that thing where you stare into space and people ask if you're okay and you say, "Yeah, I'm fine," just thinking about the fundamental nature of space-time. In 1915, he published the general theory of relativity, and this is where things get properly mind-bending. General relativity says that gravity isn't actually a force in the way Newton thought it was. Instead, massive objects bend space-time itself. Imagine space-time as a big rubber sheet stretched out flat. Now, put a bowling ball in the middle of it. The sheet dips down around the bowling ball, right? That dip is what we experience as gravity. And here's the kicker. That bending of space doesn't just affect space, it affects time too. The stronger the gravity, the more time slows down. This is called gravitational time dilation, and it happens everywhere there's gravity. Right now, time is passing slightly faster for your head than for your feet. Not much. Your feet would have to be planted for billions of years to notice even a second's difference, but it's happening. The closer you are to a massive object, the slower time passes for you relative to someone farther away. GPS satellites have to account for this. The satellites orbit about 12,000 miles above Earth's surface, where gravity is weaker and time runs faster than it does on the ground. If the GPS system didn't correct for both special and general relativistic effects, your navigation would be off by about 6 miles per day. So next time your GPS gets you lost, at least you know it's not because Einstein was wrong. Now we're ready to talk about black holes, which are basically gravitational time dilation turned up to 11. A black hole forms when a massive star, we're talking at least 20 or 30 times the mass of our sun, runs out of fuel and collapses. The star has been fighting gravity its whole life through nuclear fusion, which creates an outward pressure that balances gravity's inward pull. But when the fuel runs out, there's nothing left to fight with. Gravity wins, and it wins hard. The star collapses in on itself, and if it's massive enough, it keeps collapsing past the point where physics says, okay, that's probably far enough, and into a point where physics says, I literally don't know what happens anymore. What you end up with is an object so dense that it creates a region of space-time from which nothing can escape, not matter, not light, not information, not your hopes and dreams. This boundary is called the event horizon, and it's the point of no return. Once you cross it, you're not coming back. You couldn't come back even if you had a spaceship that could travel faster than light, because inside the event horizon, all paths lead inward. Trying to escape a black hole from inside the event horizon is like trying to go back in time. It's not just difficult, it's geometrically impossible. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our sun, though our sun will never become a black hole, it's not massive enough, the event horizon would have a radius of about 3 kilometers. That's called the Schwarzschild radius, named after Karl Schwarzschild, who worked out the math for non-rotating black holes in 1915 and 16 while serving in the German army during World War I. So, while he was stationed on the Eastern Front, he was also solving Einstein's field equations. Some people stress bake. Schwarzschild stress solved general relativity equations. Different strokes for different folks. For a supermassive black hole like the one at the center of our galaxy, which has a mass of about 4 million times our sun, the event horizon has a radius of roughly 12 million kilometers. That's about 17 times the radius of the Sunday. We actually have a picture of a supermassive black hole now. In 2019, the Event Horizon Telescope collaboration released an image of the supermassive black hole at the center of the galaxy, M87, and it was incredible. It looked exactly like what physicists predicted it would look like, a dark circle surrounded by a ring of light. Science works, people. But let's get to the really fun part. What happens to time as you approach a black hole? Imagine you're watching your friend Alice. Yes, Alice again. She's having a rough day as she falls toward a black hole. You're safely far away in your spaceship, watching through a telescope. As Alice gets closer and closer to the event horizon, something strange starts to happen. She appears to slow down. Not because she's having second thoughts, though she probably should be, but because time itself is slowing down for her from your perspective. The light coming from Alice takes longer and longer to reach you. She gets redder and dimmer as the light loses energy, climbing out of the intense gravitational field. This is called gravitational redshift, and it's the same principle that makes sirens sound lower pitched as an ambulance drives away from you, except with light instead of sound. Eventually, as Alice approaches the event horizon, she appears to freeze in place, dimming and reddening until she fades from view entirely. From your perspective, watching from far away, Alice never actually crosses the event horizon. She just gets dimmer and dimmer, taking an infinite amount of time to reach it. But here's the wild thing. From Alice's perspective, none of that happens. She doesn't feel herself slowing down. Her watch keeps ticking normally. She crosses the event horizon in a finite amount of proper time, the time measured by her own watch. From her point of view, everything seems fine, at least for a little while. She might not even notice when she crosses the event horizon, depending on the size of the black hole. For a supermassive black hole, the tidal forces at the event horizon are actually pretty mild. She could cross it while checking her phone, completely oblivious to the fact that she's past the point of no return. Of course, after she crosses, things go downhill fast. Specifically, they go downhill toward the singularity at the center. But in terms of time, Alice's clock keeps ticking normally for her. It's only when compared to clocks far away from the black hole that we see the difference. If Alice could somehow send a signal back to you, and you could count how many ticks of her clock corresponded to each tick of yours, you'd find that her clock was ticking slower and slower as she approached the event horizon. This creates one of the most bizarre scenarios in physics. Imagine Alice is falling toward a black hole while you watch from a safe distance. From your perspective, you see her slow down, freeze, and fade away, taking forever to reach the event horizon. But from her perspective, she falls right through in a few seconds or minutes or hours, depending on the black hole's mass. Both perspectives are equally valid. There's no correct answer to whether Alice crosses the event horizon quickly or slowly. It depends on who's asking. This gets even weirder when you think about the history of black holes. When a black hole forms from a collapsing star, the collapse takes a finite amount of time from the perspective of the collapsing matter. But from the perspective of someone watching from far away, the collapse appears to take forever. So from the outside, a black hole is still in the process of forming. The matter that made the black hole is still collapsing, still approaching the event horizon, still getting dimmer and redder, but never quite finishing the job. In a sense, from the outside perspective, black holes haven't finished forming yet. They're frozen mid-collapse, eternal monuments to gravitational time dilation. Now, you might be wondering, if time slows down near a black hole, could you use this for time travel? Could you orbit near a black hole for a while and then come back to find that centuries have passed on Earth? The answer is yes. Absolutely yes. This is completely legitimate physics. It's called the gravitational time dilation effect, and it's just as real as the time dilation from moving at high speeds. Here's how it would work. You get in your super advanced spaceship and fly to a black hole. You park in a stable orbit just outside the event horizon, where the gravitational field is incredibly strong. You hang out there for, say, an hour. Then you fire up your engines and fly back to Earth at a leisurely pace. When you arrive, you might find that centuries or millennia have passed on Earth. Depending on how close you were to the event horizon, you'd be a time traveler to the future. The catch, of course, is that you need an absolutely tremendous amount of energy to get into that orbit and then escape from it, and you'd better be really sure you're far enough from the event horizon that you can actually escape, because if you cut it too close, you're not coming back. The movie Interstellar, which came out in 2014, actually used this effect as a major plot point. The characters visit a planet orbiting close to a supermassive black hole called Gargantua, and time on the planet passes much more slowly than time far away. They spend a few hours on the planet, and when they return to their ship, they find that more than 20 years have passed. The science advisor for that movie was Thorne, one of the world's leading experts on black holes and gravitational physics, who won the Nobel Prize in 2017 for his work on gravitational waves. So, while the movie takes some liberties for dramatic effect, the basic physics of time dilation near black holes is spot on. Let's do some actual numbers to see how extreme this can get. The amount of time dilation depends on how close you are to the event horizon. There's a formula that tells you how much slower time passes at a certain distance from a black hole compared to time far away. At the event horizon itself, time dilation becomes infinite. Time stops completely from the perspective of a distant observer. But even before you reach the event horizon, time dilation can be enormous. For a non-rotating black hole, if you're at a distance of 1.5 times the Schwarzschild radius, that's just 50% farther from the center than the event horizon. Time runs at about 63% of the rate far from the black hole. Spend an hour there, and about an hour and a half passes far away. Not too dramatic yet. But if you're at a distance of just 1.01 times the Schwarzschild radius, hovering just 1% of a Schwarzschild radius above the event horizon, time runs at about 14% of the normal rate. Spend an hour there, and more than 7 hours pass far away. Getting more interesting. At 1.001 times the Schwarzschild radius, just 0.1% above the event horizon, time runs at about 4.5% of the normal rate. Spend an hour there, and about 22 hours pass far away. Now we're talking. As you get closer and closer to the event horizon, time dilation approaches infinity. You could hover just barely above the event horizon for what feels like 5 minutes, and when you escape back to the outside universe, you'd find that billions of years have passed. Stars have died. Galaxies have collided. Civilizations have risen and fallen. The universe has aged while you barely blinked. This is the ultimate expression of gravitational time dilation. Of course, hovering that close to a black hole would require an absolutely insane amount of thrust to avoid falling in. The acceleration you'd need to maintain your position would be enormous, and you'd experience it as gravity pushing you down into your seat. Near the event horizon, this acceleration would be so strong that it would probably squish you into a puddle. So while it's theoretically possible, it's not exactly comfortable. Now, I mentioned non-rotating black holes, but most black holes probably rotate. When something collapses to form a black hole, it usually has some angular momentum it's spinning, and that spin gets concentrated as the object shrinks. It's like a figure skater pulling their arms in to spin faster. Except, instead of a person, it's the corpse of a massive star, and instead of spinning faster, it's creating frame-dragging effects that literally pull space-time around with it. Rotating black holes are called Kerr black holes, after Roy Kerr, who worked out the math in 1963. Kerr black holes are even weirder than non-rotating ones. They have 2 event horizons instead of 1, and between them is a region called the ergosphere, where space-time itself is being dragged around the black hole. In the ergosphere, it's impossible to stand still. You're forced to move in the direction of the black hole's rotation. It's like being on a cosmic carousel that you can't get off. The ergosphere is also where you could potentially extract energy from a rotating black hole through a process called the Penrose process, proposed by Roger Penrose in 1969. Penrose won the Nobel Prize in 2020 for his work on black holes, so this is serious stuff. In the ergosphere of a rotating black hole, time dilation can be even more extreme than around a non-rotating one. The combination of gravitational time dilation and the effects of frame dragging creates regions where time passes incredibly slowly compared to the outside universe. There's even a stable orbit called the Innermost Stable Circular Orbit, or ISCO, which is the closest you can orbit without falling in. For a non-rotating black hole, this is at 3 times the Schwarzschild radius. For a maximally rotating black hole, spinning as fast as physics allows, the ISCO is at only half a Schwarzschild radius. Measured from the center, time dilation at the ISCO of a rapidly rotating black hole can be quite significant. Here's another mind-bending thought. What happens to time at the singularity, the point at the very center of a black hole where all the mass is concentrated? Well, nobody knows. Really. This is where our current theories break down. General relativity predicts that the singularity is a point of infinite density and infinite space-time curvature, where the laws of physics as we know them stop working. Time, as we understand it, probably doesn't exist at the singularity, or it exists in such a strange way that our current understanding can't describe it. Most physicists think that the singularity represents a place where we need a theory of quantum gravity, a theory that combines general relativity with quantum mechanics to really understand what's happening. We don't have such a theory yet, though there are candidates like string theory and loop quantum gravity. The singularity is nature's way of telling us, hey, you don't know everything yet, keep working on it. There's also the question of what happens inside the event horizon. From the outside, we can never see inside, so in some sense, it doesn't matter. The inside of a black hole is forever cut off from the rest of the universe. But if you fell in, not that I'm recommending this, you'd experience something utterly bizarre. Inside the event horizon, the roles of space and time actually switch. Before you cross, you can move freely in space, but are forced to move forward in time. After you cross, the singularity is in your future the way tomorrow is in your future. You can no more avoid falling into the singularity than you can avoid reaching tomorrow. It's inevitable, written into the geometry of space-time itself. The trip from the event horizon to the singularity takes a finite amount of proper time, your time, though it might not be very long. For a black hole with the mass of the Sun, it would take about 10 microseconds. For a supermassive black hole, it could take hours or days. During that time, you'd experience tidal forces that stretch you vertically and compress you horizontally, an effect affectionately known as spaghettification. Yes, that's the technical term. Well, the technical term is tidal disruption, but spaghettification is way more fun to say and means the same thing. You'd be stretched into a long, thin strand like spaghetti. It's how you'd look, not how you'd feel, because you'd probably be dead from the earlier crushing acceleration needed to hover near the event horizon, or from the tidal forces themselves, which would tear you apart at the molecular level long before you reached the singularity. Let me tell you about a fascinating proposal called the black hole information paradox, which ties into how time works near black holes. In the 1970s, Stephen Hawking calculated that black holes aren't actually perfectly black. Due to quantum effects near the event horizon, black holes emit radiation now called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly evaporate. For a typical stellar mass black hole, this process takes far longer than the current age of the universe. We're talking 10 to the 67 years or more. But eventually, the black hole would completely evaporate and disappear. Here's the paradox. If the black hole disappears, what happens to all the information about the stuff that fell into it? Quantum mechanics says information can't be destroyed, but if the black hole evaporates completely, where does the information go? This question has occupied some of the brightest minds in physics for decades. The current leading idea is that the information is somehow encoded in the Hawking radiation, though exactly how this works is still being debated. This relates to time because Hawking radiation creates a weird situation. From the outside perspective, remember, matter falling into a black hole appears to freeze at the event horizon, taking forever to cross. But the black hole also evaporates over extremely long time scales, so in some sense, the matter never quite crosses the event horizon before the black hole evaporates. The matter ends up being re-emitted as Hawking radiation. It's a quantum process, and the details are fiendishly complicated, involving stuff like entanglement and holography, and things that make regular general relativity look simple by comparison. Now let's talk about white holes, because if we're talking about weird time effects, we can't skip these. A white hole is like a black hole run in reverse. While nothing can escape from a black hole, nothing can enter a white hole. A white hole is spewing out matter and energy, and if you tried to approach one, you'd be repelled by an outward flow of stuff. White holes are solutions to Einstein's equations, just like black holes, but we've never seen one and probably never will. They're thought to be unstable and would probably collapse or explode almost immediately. But theoretically, They're interesting because they show that the equations of general relativity work both forward and backward in time. There's also something called a wormhole, which is a tunnel through space-time connecting two different points. If you've seen any science fiction movie ever, you've seen a wormhole. The idea is that you could enter one end and emerge from the other, possibly in a different part of the universe, or even at a different time. Einstein and his colleague Nathan Rosen worked out the math for wormholes back in 1935. They're sometimes called Einstein-Rosen bridges. The catch is that all known wormhole solutions require something called exotic matter with negative energy density to keep the wormhole open. We've never found any such matter, and it might not exist. So while wormholes are mathematically possible, they're probably not physically real. Sorry, Star Trek fans. But here's where it gets really interesting. Kip Thorne and his colleagues showed in the 1980s that if you could make a wormhole and keep it stable, you could turn it into a time machine. Here's how it would work. You create a wormhole with two mouths, A and B, sitting near each other. Then you take mouth B on a high-speed journey through space, while mouth A stays put. Due to time dilation from special relativity, less time passes from mouth B than from mouth A. Now you bring mouth B back. The two mouths are again near each other in space, but they're at different times. If you jump into mouth A, you emerge from mouth B in the past. Congratulations, you've built a time machine. The limitation is that you can't travel back to a time before the time machine was created, so you can't go back and stop the dinosaurs from going extinct or anything like that. Of course, this is all wildly hypothetical. Making a wormhole requires exotic matter. Keeping it stable long enough to travel through requires even more exotic matter. And the whole thing probably violates causality in ways that make the universe say, nope, I'm not allowing that. There's something called the chronology protection conjecture, proposed by Stephen Hawking in 1992, which basically says that the laws of physics conspire to prevent time machines from being created. Whenever you try to make a time machine, quantum effects create a feedback loop that destroys it. The universe really doesn't want you messing with causality. Let me bring this back to something more concrete and mind-blowing that we can actually observe: gravitational waves. In 2015, the LIGO collaboration detected gravitational waves for the first time, confirming a prediction Einstein made 100 years earlier. Gravitational waves are ripples in space-time itself, created when massive objects accelerate, usually when black holes or neutron stars orbit each other and eventually collide. These waves carry information about the extreme time dilation effects near black holes. When two black holes spiral into each other and merge, they create a region where space-time is oscillating wildly. Time dilation effects are changing rapidly as the black holes orbit. By detecting the gravitational waves from these mergers, we can study the properties of black holes and confirm that general relativity accurately describes what happens in these extreme conditions. And it does. Every gravitational wave detection has been consistent with Einstein's predictions. The man died in 1955, and we're still confirming that he was right about stuff he predicted in 1915 and 1916. That's a heck of a track record. One more cool thing about time near black holes: the no-hair theorem. This states that black holes are completely described by just three properties: mass, charge, and angular momentum. Everything else, the hair, is stripped away. It doesn't matter what fell into the black hole, whether it was hydrogen, iron, old textbooks, your ex's belongings. The black hole remembers only the total mass, charge, and spin. This relates to time because it means that the time dilation effects you experience near a black hole depend only on these three properties. You don't need to know the complete history of what fell in. Let's also talk about the cosmic speed limit. Nothing can travel faster than light in a vacuum. That's a fundamental principle of relativity. But here's a weird loophole. Space-time itself can expand or contract faster than light. During the Big Bang, space expanded much faster than light. Near black holes, space is falling inward faster than light inside the event horizon. This is why nothing can escape. Even light is being dragged inward faster than it can move outward through space. From the perspective of a photon inside the event horizon, it's still moving at the speed of light relative to the space around it, but space itself is falling inward so fast that the photon makes no outward progress. This creates truly bizarre situations. Imagine you're inside the event horizon and you shine a flashlight outward, trying to signal someone outside. The light from your flashlight is moving outward at the speed of light, but space is falling inward faster than that. The light doesn't move outward. It actually moves inward, falling toward the singularity along with you. It's like running on a treadmill that's going faster than you can run. You're moving forward on the treadmill, but you're going backward relative to the ground. So what's the practical upshot of all this? Well, for one thing, it tells us that time is not the universal absolute thing we intuitively think it is. Time is relative, flexible, and depends on gravity and motion. Every clock in the universe is ticking at its own rate, depending on its history of motion and gravitational fields. There's no universal now that everyone agrees on. Your now is different from my now, if we're in different places or moving differently. This has philosophical implications too. We tend to think of the past as fixed and the future as open, but relativity muddles this. Events that are in the future for one observer might be in the past for another if they're far enough apart and moving differently. The universe doesn't have a single, universal timeline. It has a complicated web of different timelines that intersect and overlap in ways that depend on your perspective. Black holes are the most extreme laboratories for testing these ideas. They push time dilation to its absolute limits, creating regions where time from an external perspective slows down and stops, even as time from an internal perspective keeps flowing normally. They're nature's ultimate demonstration that time is not what we thought it was. And here's the thing that blows my mind the most. All of this is real. This isn't science fiction or speculation. We have mathematical proof that these effects exist. We've measured time dilation in GPS satellites, in particle accelerators, in atomic clocks flown on airplanes. We've detected gravitational waves from black hole mergers and confirmed that they behave exactly as general relativity predicts. We've photographed the shadow of a black hole and seen the light bent around it by extreme gravity. Every prediction Einstein made about time dilation has been confirmed by experiment and observation. So the next time you're late for something, remember that you're experiencing time at a slightly different rate than everyone else, depending on your elevation and how fast you've been moving. It's not enough to matter for everyday life. The difference is tiny, measured in nanoseconds, but it's real. And if you ever find yourself near a black hole, well, you'll have the ultimate excuse for being late. Just don't get too close, or you'll never arrive at all. The study of time near black holes continues to be an active area of research. Physicists are working on understanding quantum effects near event horizons, trying to reconcile general relativity with quantum mechanics, and studying the information paradox. We're building better gravitational wave detectors that will let us observe more black hole mergers and study extreme spacetime in greater detail. The Event Horizon Telescope is planning to make movies of black holes, not just still images, which will show us how matter orbits and falls in over time. We're living in an incredible era for black hole physics. 100 years ago, black holes were purely theoretical, mathematical curiosities that emerged from Einstein's equations. 50 years ago, we'd found the first good candidates for real black holes. 20 years ago, we'd confirmed that supermassive black holes sit at the centers of most galaxies. 10 years ago, we detected gravitational waves from black hole mergers for the first time. 5 years ago, we photographed a black hole's shadow. Tonight, we're studying these objects in unprecedented detail, learning about the most extreme conditions in the universe. And through it all, the most mind-bending discovery remains this: time is not absolute. It flows at different rates in different places. Near black holes, it slows to a crawl and eventually stops from an external perspective, even as it flows normally for someone falling in. These aren't just mathematical abstractions or thought experiments. They're real physical effects that shape the universe we live in. Black holes are cosmic temples to time dilation, monuments to the strange and beautiful fact that time itself is flexible, relative, and ultimately mysterious. They remind us that the universe is far stranger than we ever imagined, and that reality operates according to principles that seem absurd to our everyday intuition, but are nevertheless mathematically elegant and experimentally confirmed. So the next time you look up at the night sky, remember that out there, somewhere, time is doing impossible things. It's stretching and compressing, speeding up and slowing down, creating regions where a second can last forever, and forever can pass in a moment. And somehow, through mathematics and observation and sheer human cleverness, we've figured out how it works. That's pretty amazing when you think about it. Good night, everyone. Thanks for coming on this journey through space, time, and the weirdest clocks in the universe. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.